second one is we're going to have some random evolution of the ellipsoid. Okay, it's convenient to have two different forms. It's just convenient. It's not a necessity, but it's convenient to have two sources of randomness. So the random lattice and random evolution of the ellipsoid. Okay, so if I start with a random lattice L of volume, which is a unit ball, then with probability 1/2, it does not contain any ball from a ball of radius 1. I take slightly smaller than 1, but I mean, think it's 1. It does not contain any balls from points from a ball of radius 1. Pretty much with good probability. Okay, so this is the starting point. And now I don't have anything, any good idea how to evolve the ellipsoid, so just do some random evolution. What is the random evolution? The ellipsoid is determined by a matrix AT, which is positive definitely symmetric matrix. So just do Brownian motion in the space of matrices. There is a canonical process called the Dyson Brownian motion, standard Brownian motion in the space of matrices, and this is what I do. So I begin with the matrix A0, which is just, ignore this factor, just identity, and I let AT to be this identity plus noise. WT is noise. But remember that I need to stop whenever I hit a non-zero lattice vector. So whenever tau1 is a stopping time, I stop my process when I reach one point on the boundary. And then what would I do? After I reach this point on the boundary, I continue the evolution, but only the subspace, linear subspace of matrices that satisfy these constraints, that preserve this point on the boundary. So I project the future, in the I step, I project the future Brownian motion on the subspace of all matrices that do not touch the vectors that are already on the boundary and continue the process. So there are many, each time I get a new point, I start a new phase. And when I lost all of my degrees of freedom and I just project to zero-dimensional space, I stop the process. And you can prove that there are not so many phases, just exponentially many phases in dimension. So this is the process. Now I define for you the process of the evolving ellipsoid. I start with a random lattice, start a ball, and do some Brownian motion, and stop when I cannot move any further. So this is the mathematical construction of the random ellipsoid that will give you that. Now I need to prove that to analyze this process. Okay, now it's a problem in standard problem in mathematics. You have a well-defined process. You need to analyze it and show that its volume is n squared. Any questions about the definition of the process of ellipsoid?
So you have this space of ellipsoids that miss all the
of these all lattice points. Yeah.
So this is not a polytope, right? It's some curved set with curved boundary.
Yeah, it's a mess. Yeah. But when you look,
but you still one smooth, I don't know, submanifold, then you continue on that, and then you hit another, and so on. Is it?
Yeah. The nice thing is that I have nice parameterization. So this space is a mess, but there is a nice parameterization using positive definite matrices. Okay, and when you look on positive definite matrices, it's not a polytope, but it's still pretty nice. Like there are facets. I mean, it's some kind of a polytope with infinitely many facets. You can view it this way. So if you look at the cone of positive infinite matrices, there is a infinite convex polytope with infinitely many facets. And you basically do random walk on that facets of this infinite volume polytope.
Nice, thank you.
Yeah. More questions? Okay, so let me show you how to analyze. So this is the problem that you can kind of a nice problem in the probability, how to analyze this process. I took really a simple one so it will be easier for me to analyze. Okay, so we can run the process till time infinity, but actually I'll stop the process at this specific time, whatever 69 minus 2 times log n. This is I'll just stop the process. And why will I stop the process this time? Because I will prove for you, I'll at least indicate, you just count how many points you absorb. That's the thing that's easier to analyze. How many points I absorb by time t. So it's e to the n squared t over 8. So this time t is exactly when you get n squared points. If you put it, you get n squared. So this is when I start the process. And what I need to show you is that the volume of the ellipsoid is basically the determinant of this matrix. I need to show you that with positive probability, actually probability 99%, the determinant of 8 is at least, at most, n over number 4, because the volume is 1 over square root. So I need to do this analysis. And the nice thing about the evolution of this matrix process is that it's a martingale. Okay, and the quadratic variation of this martingale is uniformly bounded because it's such a simple process. And so there's a nice fact that I learned from Bernard Morin that if you have a process with such small quadratic variation, you can write it as the average of two dependent Brownian motions. Okay, two dependent Brownian motions give you the you can express AT as the average of two Brownian motions which are dependent. For example, it could be that one of them is the inverse of the other. Okay, so I see that a bit over time. From here, you kind of just analyze these Brownian motions, each of them together. Sometimes you really like this fact. Some things you can analyze these things, but some things you need to use the Ito calculus to understand the evolution of the determinant. And then you get that you connect the volume to the number of boundary points. And then you analyze the probability of a point to be on the boundary. And then you reduce things to a certain one-dimensional integral. And then use the fact that you start with a random lattice. And by the Ziegler summation formula, you estimate the integral and basically you're done. So, right. So this is roughly the actual details of the proof. I did it a bit too quick. But you can read it in the paper, and the slides are on my website also if you want. I think that it's a very, the argument, the construction is pretty simple, and it could be that we could get some log factor by using something more sophisticated. But basically, I mean, I don't know how to go really above n squared, like to get something which is really above n squared seems to me either just impossible or requires something new. Okay, so my time is really up. I apologize for going over time. Thank you very much for your attention. I'm done. You can wake up. Yeah. Okay.
So I have a question.
Yeah, please.
You have two sources of randomness. One is the choice of the initial lattice, and the other one is how the ellipsoid evolves. So one is this. Random lattice. I would assume because of rotational reasons, you can fix the lattice somehow and then only have randomness in the evolution. Is that not?
Precisely. Formally, there is no advantage. Formally, you can do everything just on fix the lattice and just let the ellipsoid evolve or the other way around. Right? Formally, it's the same. It's equivalent. You can say that there is no need for two sources of randomness because they are equivalent. But somehow in the analysis, it's much better to. It helps you analyze and understand what's going on. To separate it into this and that, even though it's redundant. I completely agree with you. But it's really helpful. That's it.
I see. Formally, we can remove either one.
Either one. You can move one. It does not make sense. It's the same thing. It's kind of it's a space in the dual, and you work in both. I mean, why do you need two sources of one? But no, it helps. It helps to do the analysis.
Interesting. And is there?
Raghuvansh.
I was going to prove the bound on the other side. Putting an upper bound would be much harder. Are there some techniques that are used for that, or what are the tools used?
The upper bounds?
Yeah.
So this Kabialski-Levenstein, it's the linear programming. People use let me tell you what Blichfeld did. It's pretty nice. So he found some function on Rn. So this was before the invention of linear programming. Linear programming is from Second World War. So linear programming was not available for Blichfeld. What he did, but he basically did that still, even though it was not invented yet. So he found a function on Rn such that if you look, he showed that if you look on the sum of distances to the centers of the of this any bolts in the lattice in the packing, then the sum of distances. So you know that all these things are at least so you cannot have he just found some function and got some constraints on this function by the fact that you have packing, and this was really put on steroids with linear programming in the 70s. But these are the only techniques that I'm aware of having upper bound. Also note that all upper bounds are for any sphere packing, not for so there is no upper bound for lattice sphere packing that I'm aware of. All techniques work just for general sphere packing. It's basically the same Blichfeld and Kabialski-Levenstein idea of using kind of linear programming. A barrier function. It's a very cute paper, by the way, the Blichfeld one. I say it for the first time, like 3 pages. I mean, really nice. In English. More questions?
Over Zoom. Piyush, maybe, I think you went to the Varun Belfast, I don't know.
Sorry?
Okay, I can go first, I guess. Yeah, I just wanted to know. So you said there's this algebraic construction which is too good. Can you just repeat what do you mean by too good, and what
Okay,
are
so
these
there is
constructions doing?
okay, for example, um, my heuristic would tell you that you cannot get more than n square points on the boundary, more or less, but this is false. So there is a construction called Barnes wall construction. So basically, you take lattice that is determined by a matrix, which is like this FFT matrix. You know, this tensor product of it's a tensor product. It's a very algebraic construction,
Mm.
and that lattice has too many lattice points on the boundary. It's L3. It is L3 with too many lattice points on the boundary. It's like not more than polynomial. I think e to the log square n. And you say, oh, wow, that's an amazing lattice, right? It should give good sphere pairing, but no, it has very small volume. So both the small volume and large you call it kissing number. Kissing number is how many lattices. There's large kissing number and small volume. Okay, but this is like a sign that you don't understand everything in this space. So somehow in the space of lattices, there is the bulk and the cusp. Okay, the bulk is like we have a uniform measure. The bulk is like where most lattices live. It's like 99% are there. It's a kind of random lattice. But those are like cusps, are like tentacles going out of this space. And this is really, for me, if in the terms of probability, you don't see them. And all of these crazy constructions are there. The algebraic constructions are in the cusp, things that are very atypical for random lattice, but they exist as lattices. So this is too good to be true for me. The Barnes wall lattice is too good for me too. Like the fact that you can take tensor product, this FFT matrix type. Yeah.
So essentially, if you're again, maybe this was covered, but if you're trying to do these sort of random constructions, then we don't expect to hit the Barnes wall kissing bound with good volume.
Yeah.
Okay.
We don't expect to hit this one. Yeah.
Okay. Thank you.
We expect to hit the n. This is the number. You get the n square, and that's it. At least in the at least under some, this is what is expected. Yeah.
Okay.
Piyush, you can say.
Piyush, yeah, please.
Yeah, hi. So,
Speak up.
Yeah, can you hear me now?
Yes.
Yeah. So, is there a connection to localization in this thing of going to lower and lower dimensions?
You mean stochastic localization?
Yeah. Yeah.
Yes. Yeah. So definitely there is stochastic process. Okay. And if you're familiar with radical localization, the evolution of the matrix AT, at least it shares some similarities with the evolution of the covariance process of stochastic localization. But this is that's I think the only connection. So you don't decompose anything to this process of stochastic localization appears in many part of science. For example, it appeared in the theory of nonlinear filtering, more or less in the theory of radio FM in the 60s, 70s, whatever it is. Yeah. Right. And there is the formal so these ideas appear in many places, and it's good to know them, but you cannot just. There's no direct connection somehow.
So why is the number of phases exponential? So it's like each point gives you one extra constraint.
So it's not exactly each point one extra constraint. Dimension is n squared.
Yeah.
So the dimension of the space AT is n squared over 2.
Yeah.
Each point is one constraint, so you get. You ask about this factor 2?
No. So the number of phases was exponential.
What?
So the number of phases you said is bounded above by an exponential.
It's upper bound, right? Yeah. You're right. It's deterministically okay. You're right. Typically, yeah. This is deterministic statement.
Okay.
It's an upper bound. Yeah. Right. I never use that. It's not right. Yeah, you're right. It's misleading comment. If you know the Minkowski theorem. It's a consequence of the Minkowski theorem. You know Minkowski theorem is that you have The shortest vector. Okay, anyway, yeah, it's just
shortest, okay.
it's not an optimal bound at all. It's bound, non-probabilistic bound that holds without any relation to anything. Yeah.
But generally you expect it to be more like polynomial.
So that's an upper. Okay, the kissing number. Okay. Let me tell you what the number. For any the kissing number is never more than this number. This is guaranteed.
Yeah.
This is known from the 19th century. So that's like an upper bound for the kissing number.
Yeah.
And I don't think it was improved, by the way. You could expect it to be improved. It should be, but I don't think it was improved.
Okay.
This is just an upper bound for the kissing number. Deterministic one from 120 years ago. More. 150. I don't know. Yeah, anyway.
Yeah. Okay. Yeah. Thank you.
Okay.
More questions? Let's thank Boaz again.
Thank you very much. It was fun for me too. Bye-bye.
Bye.